Okay, and you guys are seeing one now?
Yes.
Okay, so we're going to talk about center of mass. Oh wow, look at that. It recognized my handwriting well enough to put it down in the corner. That's better than I can do sometimes. So the idea in this kind of setup is we have some kind of a shape. So here is a shape. If this is a two-dimensional shape with some kind of density, the 2D part of that, there's a tendency to call this a lamina. Which is a word that I really, frankly, couldn't care less if you knew. Think big flat thing with variable weights. Or alternatively, you can think about the weights as being thickness, and then you can think about this thing as being uniform in density. Does that sort of make sense? And what I'm going to search for is the center of mass for this thing, which is going to be the point on which I could balance it. Right? So I could put a pin underneath this thing and balance it on top of that. It's kind of good with this idea. Okay, so this is important for engineering because physics, right? Like standard statics relies on acting as though all the forces are acting on the center of mass of your object. Well, if you don't know where the center of mass of the object is, then you don't know where this kind of action is taking place. And then you have some weirdness about you can't actually calculate forces and basically nothing works. Does that thought process make sense? Okay, so
part, yeah.
I'm going to dumb this out one level. So I'm going to make a unlamina, which is just going to be two masses on a stick. You guys with me on a couple of masses on a stick? Say I have a mass of 1 over here and a mass of 3 over here. I would really like to know where I should put my kind of pin. So I'm thinking to myself, this should be maybe something here. You guys see that? Okay, so if I look up some stuff, I can figure out how long each of these two things should be. But I bet that you guys can intuit this. How long should each of these be? In other words, where should I put this little gizmo?
2/3 of the way across?
Yeah, that feels close-ish. Let me think about that. So if this thing is one mass and it's several out, I kind of need that to balance against this other side. So if you've had physics, what we're doing is we're kind of balancing this torque force and this torque force. You guys see that? It'll be in equilibrium if the two torques are equal. Does that sort of make sense? Okay, so we can take a second and figure out that that really means that the product of the mass and the distance should equal the product of the mass and the distance. So 2/3 is quite close, but not quite.
3/4.
Say that again.
3/4.
Perfect. I think it should be 3/4, a ratio of 3 on this side to 1 on that side. You guys kind of see that? That would be m1 times this distance a, or I suppose the mass at a distance a times the distance a. Right, so this is ma, mb over here. That's a distance b. It could be ma equals mb times b. You guys with me on that? Okay, so this is just telling me about these kind of lever arms, right? This would give me a way to calculate how long kind of arms should be. There's another way to approach this, which is really just to say that the center of mass should be the weighted average of the things. You guys, can I see that? This is literally what's meant by a weighted average. So how would I go about calculating the weighted average? Like, say I have a whole bunch of masses at several different points, and I've just declared an origin to be somewhere. Zero's over here. Here's M1 there, M2 there, M3, M4, up to M5. And these are at distances X1, X2 to there, X3 to here. I guess I should do that this way. X4 to this one. Well, I guess I put dots and then I counted to 5. Whoopsie daisies. So let's call that MN. Put some dots. This one is at XM. So how would I formulate a weighted average? No?
Add up all
Right.
those stuff and divide by the number of stuff.
Yeah, that's exactly what we do, right? To calculate an average, we'd add up the stuff. So I'd add up the xi's, right? I do this sum over I is, oops, I guess I started these at 1. Right, so I'd add up the kind of distances and then I'd divide by the total, right? Now, in a weighted average, I should add up the, what am I weighting by? I guess I should properly call this a massed average rather than a weighted average. So I'm going to add up mi times xi, and then I'm going to divide by the total mass. Does that make any sense at all? Okay, so this thing happens so often that we have kind of special words for it. So this bottom thing, we have a special word for that's not very complex. This is the total mass. Everybody on board with that one? It's not, I know it's not very creative, but it is what it is. All right, how about my MIXIs? Does anybody recognize that from physics?
That's a moment, isn't it?
Yeah, this is what's called a first moment. It's called moment. Huh? So why is it the first moment? I don't know, I'm not a physicist. There's a second moment that you use to calculate torque. Or, sorry, use first moments for torque, use second moments for, I don't know, I'm not a physicist. Say again?
It's moment of inertia. That's the second moment. That's for rotational energy.
Yes. Yeah. The second moment is about rotation. This one's just about balance. You guys good with that? So I'm kind of off on the side here. I'm doing discrete things, right? Which are sort of garbage. Because my lamina that I wanted to talk about initially has some density, right? So I have a problem. thus far not managing to actually calculate the thing I wanted to calculate. Right? Because so far I only have finitely many pieces, and I'd really like to move to a continuous thing. So what's going to be my analogy of the first moment? What's the analogy of adding up?
Oh, integral, I'm assuming is what you're looking for.
Yeah, so I'm going to end up double integrating. And I'm going to double integrate x. And I guess I'm going to call this density function rho of x and y. That's a rho, not a p. Rho. I know it looks like a p. It's a rho. As in row your boat. Okay, so I'm going to add this up d area. Now, the confusing thing, the only really confusing thing about this section is that we're adding up x's weighted by density, right? A density times an area is going to be a mass. So this guy here is playing the role of mass. You guys see that? So this is a mass times an x distance. So this is kind of what I was thinking of over here, right? This is the weighted average in x. Except that I haven't actually calculated the average part of it yet. You guys see that?
Mm-hmm.
So I need a little bit more. And in order to get that little bit more, I'm just going to label this thing. I'm going to call this my. And the reason for that is awful. I don't quite know why this is the chosen notation, but it is. It's, well, okay, I do kind of know. So this is tendency to be unbalanced with regard to y. Right, this is like for a fixed y, our tendency to be unbalanced. This notation does not make me particularly happy, but it is what it is. So then the center of mass, right, in the x direction should be the x average. So the total kind of moment is the double integral of x rho of x and y d area. And then what do I need to divide by to get the weighted average? Over here I had the kind of moment bit, right, on top. And then I divided by the total mass. How do I calculate the total mass of my lamina?
Integrate your density function.
Okay, we're just going to do the double integral of the density function. And I haven't really said what I'm double integrating over. So I'm just going to call this lamina L. And we're just going to say, all right, you just double integrate over L in whatever coordinate system is convenient. Does that make sense?
Yeah.
Okay, so this is where the X center of mass is. Where's the Y center of mass going to be?
The same thing, but with y instead of x.
Yep, exactly the same thing. So we're going to double integrate over our lamina, y, rho of x and y, d area. And then we're going to divide by the total mass, which is going to be the double integral of the lamina of rho of x and y, dA. And this top thing, again, we're going to call by this completely bizarre, we're going to call that one mx. It's the x moment and it's calculated by averaging y's. The y moment is calculated by averaging x's. It's awful. I kind of hate it. I'm sorry. Any questions about this kind of broad idea?
I actually have a question about the moment itself.
Sure.
If you just took the moment, what would that give you? Like, what is the value of the moment without averaging it?
Yeah, that's a solid question. So let's think about the units on it just for kicks. So it's masses times distances, right? So it's gonna be the sum of all the, like, in reasonable units it would be kilogram meters, right?
Mm-hmm.
So it's going to be the total kilogram meters involved in the system, which to me doesn't have an obvious physical interpretation.
Yeah. Okay.
Yeah.
That's what I thought. I spent about 2 hours yesterday trying to figure out what it was. Like, trying to find a physical representation for it, like what it means.
Yeah, I haven't personally run across a useful physical interpretation of it. That's not to say there isn't one. I'm open to finding one, but I don't know one off the top of my head.
Okay.
One thing that might be kind of interesting, at least, that you could learn just from calculating that number, would be that if you had two systems with the same amount of mass in them, but vastly different moments, then you could maybe say something about this system. But frankly, I think it would amount to how spread out is it. Let's see, does that make sense? No, broadly speaking, that makes no sense at all. So, yeah, I'm not aware of a good physical interpretation.
Okay. Good to know. I'm not like just bad at physics and math.
I mean, I will definitely say at least that physics is not my strong suit. The amount of physics training I've had is not enormous. Right? Oh God. Oh no.